Yes, yes. We're going to use the transformation TV and we're going to move this sphere, this little red circular thing. And here's your TV transformation, that little black arrow. So we're going to move this much. And we want to know what is the new equation for a sphere. Just an FYI, when it comes to a sphere, it's a lot like a circle, but instead of an X and a Y, there's a Z because it's three-dimensional. So it ends up being X minus H squared plus Y minus K squared plus Z minus, what letter do you want to go with? I sounds great. Minus I squared equals R squared. Because the radius of a sphere doesn't change. It's just a whole bunch of circles on it. So it doesn't have to be like R cubed. It's still R squared. Yep. So there you go. So that's what the sphere equation would be. And then just using that knowledge. So again, we're using what we learned. Was that number one? Yeah, in example one, the TV. We're moving a point in three-dimensional space by X plus 1, Y plus 3, and Z plus 5. All right. Just like in the line and in the plane, you can think of these as X prime, Y prime, and Z prime to represent the new points. And this would be taking the old points, doing something to them to get the new points. So when we write our three equations in our first step here, it'd be X prime equals X plus 1. So if you knew what the old points were, I can just add 1. Now I have the new points. However, I want to know how to find the old points. So let's say you knew the new points. To find the old points, how would I solve for X? By doing what? Correct, but how? Subtracting. All right, so I told you probably already knew that, but a lot of students I've seen so far are just doing plus 1. You got to change the operation. So if you're adding, it needs to be a subtraction. Yes, sir? No, we're trying to produce a new sphere equation. So we're going to move this guy this many units. So somewhere right here is going to be like a new sphere. I need to know what that equation is. I already have this equation. It gave it to me. But now I got to figure out where is the new sphere going to be located if I translate it this long or distance or whatever. What would that new equation be? That's what we're trying to produce. So to do that, I now know that X would equal the new point minus 1. Then we do the same thing with the next one. Y prime equals Y plus 3. So how would I find the old point? Subtract the 3. So now I get Y prime minus 3 equals my Y. There's my first point, or my first equation, my second equation. Now we just got to do it with Z. So now I get Z prime equals Z plus 5. How would I solve this one? Subtract 5. So now I get Z prime minus 5 equals Z. Take these three equations, and now you're going to substitute it in for the X, Y, and Z so that we're able to produce our new sphere equation. So I'm going to put this work over here. So my X, I'm going to plug in X prime minus 1. So X prime minus 1. But there was already a minus 1 there, so it becomes a minus 1. So it'll be an X minus 1. So then this part again right here, I replaced X, correct? But then there was already a minus 1 there, so that minus 1 still stays there. So then you take the Y, do the same thing. I'm going to replace Y with Y, sorry, where is it? Y prime minus 3. So Y prime minus 3. Again, there's already a minus 3 there, so it becomes a minus 3 minus 3. plus I replace the z with the z prime minus 5. There was no other things being added or subtracted, so I can just leave it like this. All you got to do now is just simplify. Minus 1 gives me what? Very good. Minus 3 gives me. And then there was nothing I could do here. You now produced a new sphere equation. So if I was to shift this over, this is its new location. No. It's just understanding this transformation here. It's a lot of notation, a lot of writing. But no, not too much math. Yeah, yesterday kind of hit me hard that morning. It's just all clogged up. And now with the wind advisory, that policy is going to keep moving. So it is what it is. Any questions though? All right, let's keep talking about this discussion as we look at number 4 of the exercise. So in exercise 4A, given the sphere above the equation there, we just want to figure out what the center and the radius is. So if we knew that our center last time was h comma k, predicting, what do you think the center of a sphere would be here? Okay, and then how would you find each one of those numbers? How so? Okay, yes. Look at the number, that's a number, right? Correct, but what do you do with that number that's associated inside? Huh? How would I pull the center out? Not quite. Not subtract them out. Not make a good. You have to flip the sign. Remember, the formula for a circle and a sphere is x minus h squared plus y minus k squared plus z minus I squared equals R squared. When you have a minus inside of a formula, to pull out the correct number, it has to be its opposite sign. Because what you're doing here for this x plus 3, this is the same thing as x minus a negative 3, correct? So therefore, the negative 3 would be the actual h value. So instead of having to rewrite it, you just change the sign of it, all of it. See, we were rewriting the equation. A is just asking us to locate the center and the radius. It did not ask us to find the center of the last question. So last question, we were looking for a new equation. This question, just looking for the center and radius. So my center then would be what? Negative 3 comma positive 1 comma positive 3. Just like that. So you just got to know, you just got to change the sign and you have it. What if there wasn't a number? So let's take the example from the last one, that it was just a z squared. What would the I be in that situation? A 0. Don't leave it blank. It's still a 0. It's still a value. Good. All right. Just like a circle, what would the radius be here? Good. This right here is r squared equals 10. So if I want to know what r is, just like with a circle, I still got to take the square root. Now, in this situation, I don't have a square root of 10, so I just leave it as is. Yes, sir. Yeah, this right here is r squared. So yeah, so you basically just take the square root of whatever that number is at the end of the equation, and that would be the radius. Because in the formula, the radius is r squared. So if I want to know what, it's get the r. That's right. That's right. Yes, sir. We good with that? I'm finding the center and the radius of a sphere. That's it. Yeah, that's it. It's supposed to be. Yeah, not trying to make it hard. I'm trying to show you the easiest thing. So it's just like a circle. It's just instead of a circle having 2 coordinates for a center, the center of a sphere will have 3 points because it's 3-dimensional. It has a z-plane now. All good? All right. Let's look at part B. This one now says write a vector and its associated translation map that would take the sphere to its image centered at the origin. Meaning, I need to produce a matrix. Well, what do you want to call it? I need just one letter. L, that's fine. A is fine. B is fine. Q, whatever letter you want. We're just going to call it whatever letter. Again, you get to name this part. Didn't tell us what to name it. But I'm trying to figure out a transformation. So I need to do something with the X, I need to do something with the Y, and do something with the Z. So that basically the center, which was -3, 1, 3, turns into, it said the origin? Yeah. So what's the origin for a three-dimensional space? So think of this logically. Don't overthink it. What do I need to do with the X value to make it 0? +3. So this is my first transformation. What do I need to do to the Y to make it 0? Subtract 1. Very good. And then the Z, what do I need to do to Z to make it 0? Subtract 3. You've now produced a transformation that would take that original equation to the center. Okay. Not trying to make, it's not supposed to be complicated. It's new. This is all new, right? We're not going to go into complicated stuff until you understand new. This would be different if you learn this like in Algebra 2 and I'm supposed to take the next step. This is the first step. Questions on this? All right. Okay. Again, if you think it's too easy or you're waiting for that shoe to drop, just keep waiting. All right. Example 2, let's talk about how to find the magnitude. What's magnitude mean? Distance from. Well, vector tells you distance and direction, but magnitude is just distance from the origin. Let's talk about how to find the distance of a three-dimensional shape. So there's a beautiful shape that I don't have to draw, which is fine by me. It's not on y'all's. Oh, okay. From the center, you can just take one singular point from this sphere. Let's take the sphere, for example. You just have to take one single point. Easiest point would be the center. Because if I can find the distance from the center, then I'll find the distance of all of them. So it'll be the same distance. If I move the center to the origin, then the distance over here, it might be in the negatives now, but it'll be the same distance to move here. So if we just take one singular point and we start from the origin, the best one to do is the center point. That's exactly what we'll deal with. So for this one here, define a general formula for the magnitude. They use this notation z squared here. Oh, okay. Oh, we're leading into it. Okay, I see. Okay. So if you wanted a, what's these double brackets mean here? It means magnitude. So this is now magnitude squared. So I'm going to lead into what the actual equation is on part B. But this right here would be the same thing as a squared plus b squared. Oh, my bad. XYZ. Let's keep it accurate with this thing here. X squared plus y squared plus z squared. So if this is what the magnitude squared is, how would I actually find out what the magnitude is? Square root all that. So instead of it now being the square root of a squared plus b squared for a three-dimensional space, it's just going to be the square root of x squared plus y squared plus z squared. Now you have a distance formula for 3 dimensions. This pattern actually continues. So if you were in fourth dimensional space, you would just have a w squared, and then so on and so on and so on. Any questions on the formula for magnitude of three-dimensional shapes? Awesome. All right. So this will be the last little exercise question, and then it has a nice little chart for us to kind of organize all information to wrap this up. So in exercise 5 through 8. So on number 5, which vector has the greatest magnitude, V or U? Quickly, for the next 1 to 2 minutes, go ahead and find the magnitude of V and U using that formula I just provided. And let's determine which one has a larger magnitude. Good. So let's look at this. Make sure we're all on the same page. So the magnitude of V, we now know it's just going to be x squared plus y squared plus z squared. So this will just be 0 squared plus 5 squared plus -4 squared. Again, if you do use the calculator, make sure you're putting your negative number in parentheses so it's squaring it, so you don't end up with a negative number. 0 squared is 0. 5 squared is -4 squared is positive 16. Good. So therefore, 0 plus 25 plus 16 gives me 41. Now let's go find the magnitude of U. Square root of 3 squared plus -4 squared plus 4 squared. 3 squared is -4 squared is 4 squared is still 16. 16 plus 16 is 32 plus 9, 41. So yes, they are equal. Very good. Anybody have any questions on that math? All right. So on number 6, explain to me why you think vectors in three-dimensional space can have equal magnitude, but a different vector. Perfect. They can have the same size. They can have the same size, but be going in different directions. I think I started spelling direction in the middle of difference. All right. So yes, so again, we've learned even with two-dimensional space is we can have two vectors going in opposite direction, but actually be the same distance. All right, so let's talk about this little chart, and then we'll do one little last problem. And that's pretty much all that I got for today. So any questions up to this point? If it feels easy, it's supposed to be easy. Hannah? It's supposed to be awfully easy, huh? You asking me how many word problems there are? Not much. Yeah, we'll just add a step, but just one step at a time. One step at a time. So at the end of this, yeah, you might be doing like 10 steps to do a problem, but you had easily progressed to get there. So it's not going to feel like it. I'm going to trick you into doing a lot of work, but making it feel like it wasn't. That's the goal, at least. All right. I thought you asked how many word problems there are. I was like, the one stressor in our lives. All right. So, okay. So we have basically analyzed two-dimensional space in the last 3 units. So we have our component form. which is just the inequalities with the A and B. We have our column form, also known as a 2x1 matrix. We have our magnitude formula for two dimensionals. We have our addition equation. So again, adding two vectors, you just add their corresponding x values and y values. We have our subtraction, same concept, subtract the corresponding x values and y values. Again, we also noted in addition, it was commutative. The order didn't matter. So v plus u is u plus v. But in subtraction, we learned that it is not commutative. The order does matter here. And then we also talked about scalar multiple. If I have a number outside the vector, I just have to multiply the x and the y. All right, this was talked about in the last, I think, 2 or 3 lessons. So now let's have our generic formulas for our 3-dimensional space. And it acts just as 2-dimensional space. So what do you think the column, and you can see, it gives you the component form. It's same process, but now in ABC. So what do you think the column form would be, but in a vertical format? And we already talked about this. What is the magnitude of a 3-dimensional shape? Perfect. Square root of a squared plus b squared plus c squared. What do you think is going to be the rule? So if, let's go with this, if v equals a, b, c, and u equals, that's good, d, e, f, then v plus u would equal what? Perfect. We're still going to add their corresponding place values. So this would now be A plus D, comma, B plus E, comma, C plus F. Questions on that? It's the same concept with subtraction. So once again, if V is equal to A, B, C, and U is equal to D, E, F, then V minus U would be A minus D, column, B minus E, column, C minus F. That is because that's how components are. So for vectors, we have to use these inequalities so that when we graph, we actually have like a ray or a line segment of a ray, versus parentheses would just be a coordinate. There's a difference between the two. One is just a single point. One is like a ray in space. Doesn't equal the greater than or less than. Oh, that means equal to. And there was like a white dot that was and there was not equal to, equal to. What else was here? Is this it? What was the question? Yeah. So was the question asking like, what's the domain or something? Okay, so let's hypothetically say this is a 1, and let's say this is a 7. Yeah. And you had to figure out what the answer was. So it'd just be 1 less than, but no equal to underneath it because I'm not including it. I'm just going to go with X. I don't know what you're dealing with. Less than or equal to, because now 7 is part of the solution. Equal to, and the open is mean not equal to. I can be all the numbers leading up to that number, but not including that number. That is just an FYI. This is a 7th grade question. You also saw it in 8th, Algebra 1, Algebra 2, and then I don't know, we don't deal too much with inequalities here, but you would see it here as well. Yeah, equal to is filled in. Yep. On this last one here, it's all right. It's a good question. Is that who y'all had for 8th grade? I was trying to figure out y'all's grade level, who y'all's 8th grade was, a teacher was. Because I know Wallace was there, but then I was like, was that before or after y'all left? Gotcha. All right, so any questions on three-dimensional space? Okay, let's do one more question, and then I got nothing else for today. If you haven't finished those 3 assignment or 4 questions up there, you'll have time to do that today as well. I did not, but I can grade it for you so that you don't have to stress about it. All right, number 8, it says, given these 2 vectors, we're going to calculate the following. So I want you to go ahead and try to do I, 1, 2, and 3 in Roman numerals, and then we'll come together, talk about it, and then do B. Good? All right. So V plus U, again, you're just adding the corresponding values. So you should have gotten 2 plus -1, which gives you 1. 0 plus 5, which gives you 5. -4 plus 3, which gives you perfect. Any questions on that? All right. 2V minus U, what do you think you have to do first? Multiply by 2 first, and then subtract. Order of operations, PEMDAS, right? You got to multiply before you add and subtract. So 2 times 2 is 4, minus -1 would be 5. So this would be 2 times 2 minus a -1. So that would make it a positive. So this will give you 5. 2 times 0, 0 minus 5, -5. 2 times -4, -8 minus 3, -11. So make sure you carry that minus with each number. What does this mean? Magnitude, which is the distance. So I'm going to do the square root of -1 squared is 5 squared is 9 squared is 9 plus 1 is 10. 10 plus 25 is what's up? Yes. My bad. 3 squared would be 9. Okay. And then 9 plus 1 is 10. 10 plus 25 is 35. Cool. That's what you did? Yeah, it just makes that number sense part, right? 35 can't break down. It goes to 5 and 7. Doesn't help me with anything. Questions on how to do the math? All right, let's do 8 or part B here. Let's suppose this is going to be a rough guess. Suppose we have a point in space 1, 3, 5. And then I want to translate V then by U. If I do V then U, I'm basically doing what? If I take a point in space and I move it by V and then I move it by U, I'm basically moving it by, Okay, kind of, but a little bit more specific. There it is right there, the distance from V plus U. So since I've already done the math for V plus U, I don't have to take this point and add the V, then add the U. I can just go straight to the V plus U. So let's say I add this V plus U. So this is V plus U, hypothetically. This is hypothetically. And I move it to some other point. Now, before I go look for that other point, let's actually read the question. Suppose this point is translated by this. We want to determine a vector W that would return this point back to 1, 3, 5. What do you think I'm going to have to do? Negative V minus U, very good. But instead of doing the negative V minus U and doing the math, what am I really doing? I like where you're at with that. There it is. The negative V minus U would be the same thing as the opposite vector. What we learned yesterday or the day before, I can't remember, but the opposite of that. So you're not wrong by saying negative V minus U, but it would be the opposite. So instead of to do the math, I can just take this question right here and just find their opposite vector. So what's the opposite vector of this guy? And 1. Perfect. So if I applied this vector to this point, it would take me back to my original point. So instead of doing more work, always figure out what is the question actually asking, right? Most of y'all would have taken 1, 3, 5, added the V, then you would add it the U, and then you would have been like, all right, now how do I get to this point to this point? And you would have to do some little math, and you probably got to this conclusion as well, but go to where the question's actually asking. Any other questions there? That is all that I got. With the extra time, how long do we got